Hello everyone, welcome back to my tutorial. In this tutorial we are going to do centrifugal analysis of disk. We have taken a material of mild steel of Young's modulus 210 gigapascal, Poisson ratio is 0.3 and density is 7850 kg per meter cube. We are going to do linear static analysis. In this case I am going to take quarter symmetry. That means quarter model I am going to take will do analysis. So this is my model. So and this dimension is, so this model I have created already. Here the dimension is 50. This dimension is 50 mm and this dimension is 125 mm. And this thickness is 10 mm. So this is our model. I have already created this model and saved in step file. We'll directly open the step file and we'll do the analysis. So this is actually rotating disk. I'm going to take only the quarter model. So this is the analytical result. The disk is rotating in the speed of 500 rpm. This value we are going to apply as a angular velocity of 52 radian per second. So these are the dimensions: 50 mm, 125 mm, radius is 50 mm. Okay. Now we'll solve this problem using salome meca. First open the salome meca. Salome meca is the open source and free finite element analysis which is available in Linux as well as Windows. Now I'm just going for geometry model. First I have already created the model and saved the file, so I am going to use import option to import the file. I just saved as a step file. Go to file, import, step, pictures, code aster, rotating disk. This is my file. I'm just opening here. It has to consider millimeter, just saying yes. Now we'll check the dimension. Go to inspection, dimension, bounding box. So this is actually a dimension. 125 mm is the length. It is converted to meter is 0.125. So everything is converted in meter. Now it is in meter. Now just close it. Now we'll save this file. I'm just saving as steady 5, save it. Now we'll create the groups to apply the boundary condition. Now just go to the model here. Now I'm going to solve this model in quarter symmetry. Salome meca doesn't have any symmetry boundary condition. Whatever the normal to the surface, that displacement I'm going to arrest is to apply the symmetry boundary condition. So volume group, select all, disk, just apply it, face group, go to fit screen, just rotate it here. To proper rotation, you just press and hold the shift button and rotate it. Now this one is the X symmetry. Just select the surface, add. I'm just going to give symmetry in X, apply. Select the surface, add. This is actually symmetry in Z. Symmetry in Z. Then apply it. To avoid the free body motion, we need to arrest one more degree, that is y direction. So I'm going to arrest this point in y direction. Go to point, select this point, add, fix in y, apply and close. Now symmetry in X, the surface normal to the direction is, here you can see X. Symmetry in Y, the normal to direction is Z. So that is the displacement we are going to arrest. Now we have created the groups. Then we'll save this file. We'll go for meshing. Go to mesh, select the revolution, mesh, create mesh. Choose the NetGen 1D, 2D, 3D. Choose here simple parameter. Here I am giving 0.005. Just say OK and apply and close. Right click this mesh one, compute. Now we have created the mesh. This is a linear tetra element. If you want to go for higher order also, we can go for. So now I'll just go here, check the groups. So we have one fix y is the point group, symmetry x, symmetry z. This is the volume group. Now we'll save this file. We'll go for aster study to create the setup in code aster. I'm just going for aster study. I'm going to use stable version. So first add one by one. Add stage. Go to mesh. Read the mesh first. So this is the mesh. MED format. Just apply it. Save OK. Then model definition. This is the finite element model. Finite element. Everywhere we can apply. Choose mechanic. 3D element. Just save OK. Apply. Save OK. Now model definition is done. Go for material. First we need to define the material. Linear isotropic material. This is 210 e power 9. You have to. This is 0.3. Density is 7850. Now just say OK. Then just apply it. OK. Now we have created the material. Now we need to assign the material to the mesh. Go here. There is assign material. Go to mesh. Choose the mesh. We are assigning model also. We are assigning. Then we need to choose the material. Everywhere choose material. This is our material. Save OK. Just apply it. Now we have assigned the material to the mesh group. So we have assigned the material. Now there is no functions or list are required. Just go to boundary conditions. Assign a mechanical load. Here we can choose enforce DOF. Click it here. Add. First there is a group name. So just go to element group. Edit. Symmetry X. Just say OK. We need to fix in X direction. Just fix it here. Save OK. Now there is one more boundary condition. Just go to edit. Edit. Choose symmetry Z. Save OK. Now we need to fix it in Z direction because that is symmetry Z. Save OK. Now there is one more boundary condition. We need to arrest the node. Just go to edit. So there is option called group of nodes. Edit. So fix in Y direction. Make sure you have ticked it. Just say OK. We need to arrest Y direction. Make it 0. Now we have arrested the model completely. Now we need to apply rotation. So the disk is rotating in the speed of, here you can see 500 rpm. By converting that into SI unit of radian per second, so pi by 30 into n by rpm, so it is coming 52.35 radians. So now you just go, there is option called rotation. Edit. So celerity is nothing but rotational speed, that is 52.35. Axis, just click it here. In which axis about it's rotating, just click it here. It's rotating about Y axis. So this third one is the Y, just make it 1. Second one is the Y, make it 1. Remaining we make it 0. Now there is option called center. Just click it here. Make it this. Center is 0, 0. So this is the center. This is a center point, and about which axis it's rotating is y axis. So the two things we need to specify here, and the remaining third one is we need to specify the angular velocity in radian per second 52.35, because I am using SI unit, everything in, so 52.35. Now I have specified everything. Now just say OK. Now just apply it. Now see, we applied symmetry x, that means this surface we have applied x direction displacement 0, and symmetry z means this surface, sorry, this one is the symmetry x and this one is the symmetry z. And fix y node group, this particular node we have applied fixed in y direction, and we are applied the center point is 0 0 0 and the axis about rotation is y axis, and the value is angular velocity is 52.35 radian per second. Everything we have specified. Now just say OK, then just apply it. Now we have defined the load and boundary condition, everything. Now we'll go for analysis, static analysis. Now choose the material field and model is this one. Now here we need to choose loads. Go here, edit, this is the load, say OK, apply, say OK. Now we have defined the solver. Now we need to go for post processing, calc champ, we need to calculate the von Mises stress, Reslin. So I'm just here, we can choose directional stress as sigma element and sigma node. This is elemental directional stresses, nodal directional stresses. So sigma x, sigma y, sigma z, everything it will calculate. In criteria we can calculate von Mises stress and principal stresses. I'm going to use the command called SAEQ element, SAEQ node. This is enough. If you want to calculate reaction force and nodal forces, we can go for force. That is I'm not going to use. Go to model and material, say apply, say OK. Now I am calculating the post processing. Now we'll go for output, save the output results. So there is no name, just click it here, go here, pictures, code aster, rotating this. I'm going to do centrifugal underscore RMAD. This is the result name, dot RMAD. Just save it, just apply it. Just close this. Here we need to specify it actually. Edit, mesh file, Reslin, we have to choose it as calc champ. Here there is one more option, tau champ, make it S. Just say OK. Format to make it MED, just apply it. Now see, there is no error coming because we are not defined results here. We need to define this mesh result. This will only calculate displacement. So here only we are calculating stress and displacement, everything. So this one, and tau chum make it S. Instead we can go for nam chum also. We need to choose one by one. Tau chum making S means whatever the results we are calculating in calc chum, every result it will save it here. So just make it OK, just apply and OK. Now we have defined the setup. No error because there is no red color is showing. Just go for history view, plus button, click this pin, go here, 5 seconds, make it run. Before that it has to save this file. Just OK, just save the study, run it. Now it is solved without an error. Now we'll open this file and view the stress. Now just go to paraview, just open, pictures, code aster. There is a rotating disk. I have given centrifugal.rmd. Just select this file, just say OK. Here you can see every results are came, just apply it. So this is our result file. Just go here, displacement, rotating about y. So this is the result. Now this is actually result magnitude. This is rotating about y. Now now we'll change the, go to von Mises's SIEQ node. Just go here, von Mises. This is actually a von Mises stress. Now we'll check the von Mises results here. So now we'll change the value, the color pattern to blue to red. Blue to red rainbow. Just apply and close. Here I am making it to 12. So this is the pattern. Now we are getting a stress value of 2.8 e power 5. So we'll compare the results with here. So megapascal, 0.28 megapascal is nothing but 2.8 e per 5. So the same value we are getting. So this is the von Mises stress. Now just go here. Actually we are modeled only quartile. We can view this value, we can reflect this value in full model. Now we just go to filters, search. There is an option called reflect. So choose this reflect, just enter it. Now it is reflect came. So how we can choose is, see this surface is in the plane of x and y. Now we need to reflect in z direction. So just choose z here, just apply it. Now see, it has reflected. Now we just keep this reflect 1. Now we just want to reflect the results this side also. For that, just check this plane. This plane is in y and z. That means we need to choose reflect in x axis. Select this reflect 1, go to reflect again. Reflect again. Now we need to choose x axis. Choose the x. Then again apply it. Now see. So this is the full disk results. This way we can reflect it and we can view the results for full model. If you want to clip the model into off, we can use clip. In which direction you want to clip, we can clip it. Here it's showing this way. If you want to change this one, normal x, normal z, again you just give. Same way we can clip it. So this is one. Again you just go for clip. Now we just make it normal. Just clip it again. Now see, just remove those planes. This is the quarter results. Similarly we can go for full model as well as quarter model. So as results, as we have calculated only for quarter model, now we have visualizing the values in full models. So using reflect options. If you want to check the results for in a particular node, we can use the option called view, windows, selection display. Make sure you have selected this selection display inspector. That will show here. Just go here, choose the equivalent value, equivalent node. Now we can choose any one of the node here. That value will display here. Just select here. So not this one. Using node option, there is an option called node. Select this one. Actually I have selected more nodes. to deselect. So only yes, only one node I have selected. Now one versus test is the first value is 2.78 e power 5 is coming. So says almost very close to 2.8. So this node it's getting 2.78. So like this we can check the value. To add this value, just go here. So in this tutorial we have learned how to apply centrifugal load to the disk or the analysis of rotating disk. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.